Okay, thank you, Shinnok. So hi everyone. My name is Fred, and I think for people in have attended the session one software, you've probably heard about my colleagues Harper and Shinnok talking briefly about the application of the software we've developed, and today, and hope you found interested about those their talks. And like for my talk, I will be more focused on the methodology of the package and the ration explain to you what the rationale behind the software. So the package is called bulk LMM. And for my talk today, I will go over briefly about what it is and how the methods will work. And next, I'm going to show you some performance results. And finally, I will conclude my talk with discussions on the strengths, limitations, and our future works. So what is actually what we call it bulk MM, and what is it? It's a package written in the programming language Julia, and we designed it to be able to perform fast genome scans over large number of traits using the linear mixed models. And it's the package is right now published and downloadable through Julia registry, and with our source code open on GitHub at this um, in this URL. So next, I'm going to move on to talk about like the things. What will be the data suitable for to be analyzed using our framework, and what motivates us to develop such a tool. And in the following data it measures the liver proteome on the individual level with on the BXD mice with multiple individuals indicated by like these for with the same strand BXD9, and so it's better to account for the sample relatedness between these measurements introduced by the known strand structures, like here. And so how can we account for the sample relatedness? We apply the linear mixed model framework on the trait measurements Y here, with the mean determined by the fixed effects X0, beta 0, and which is the non-genetic effects, and XG, beta G stands for the effects of the marker we're interested. And in the linear mixed model, we introduced the random relatedness to the random effects U here, where the correlation structure is defined in the kinship in the matrix called we usually refer to as the kinship matrix, where each element measures how across all markers how individuals are related. So these statistical model can be viewed as this as such, where like the trait Y follows the normal distribution with the variance components contributed by two components from the random effects, and the other parts from the normal error effect. And so we can further we parameterize the we denote the variance in the traits expand by the genetic variant to be sigma g, a square g, and we also denote the variance unexpand by the sigma square e here, and then we can reparameterize it using the h square, which is usually referred to as the heritability, stands for the proportion of the variance expanded by genetic variance of the total variance. So for each test, we're using the metric of log scores, testing whether the marker effect actually exists. So to evaluate such a model, the classic steps consist of the following. The first step is to decorrelate the traits by the eigendecomposition of the kinship matrix, which defines the correlation structure. And then for a given heritability h square, we construct the weight, and we can reweight the data so that they will have the traits denoted as the y stagger here will have equal variances, and then we can write out the function the log latitude function of the y dagger as a weight containing the weights, and where the weights is determined by the h square, so that the log latitude can be written as a function of the only parameter h square because we write it for each given h square. And finally, the last step is to maximize the objective function on the h square. So basically, we will estimate as the h square that gives us the best value of the objective function. So our main innovations mainly come to play as the approaches to speed up the processes to evaluate such a linear mixed model, particularly for many traits and markers. So we first noticed that the loss score for testing the association between the trait and the marker can be written in this form. And under the linear regression testing one marker effect, then it can be further written as a function with only the Pearson correlation between the trait and the marker. And also, after some standardization, we noticed that the pairwise correlation for many traits and markers. So not only one can be, they can be efficiently computed using the matrix product of the Y star here and the G star here, where basically each column of each matrix being a trait or a marker. Then we may compute the loss scores by just computing this matrix of pairwise correlations, and then map each element to get the loss scores for not one pair of the trait and marker, but all pairs efficiently using this framework. But as I mentioned, this under the case of linear models, can we apply this convenient effect to linear mixed models? To actually extend these effects to linear mixed models, we go back to the framework of evaluating the linear mixed the model. Then we notice that once we've been given the h square, and after we construct the weight, the weighted data is actually can be modeled using linear models, such that this leads us to some important observations. The remaining steps, and also it's the key step, is to get the estimate of heritability under this scheme. And if we don't require the heritability to be differed by marker, that meaning that we will be re-estimate it under when testing all markers, but we can use the estimate of the heritability under the null for each trait, then apply to test all markers for that trait, for the association with that trait. Then we don't need to re-estimate when testing all markers. And furthermore, if we may not even care about the small differences of the heritability estimates for across the traits, then for some traits they might share the same estimates of heritability, and we can construct the same weight, and using the same after applying the same transformation, we can compute the loss scores for the traits, the many traits together, sharing the same estimates of heritability. Then based on this shortcut, our fasting methods called null grade, these will estimate heritability for many traits under the null model for the heritability, and also the estimation is using a grid search approach. So exactly how would it work can be demonstrated by the following toy example. And suppose we have 6 traits, then we first estimate each for each trait under the null model using the grid search on the grid of just in this toy example, just 3 values. Can be taken values from 0, 0.5, and 0.95. Then after the first step, estimating from null model, get the h square. Then suppose that these two share the same estimate of h squared. Then we can process the first 2 traits and to get the loss scores together for these 2 traits, and similarly for other groups of traits. So next we would like to show you some results of our methods. So the first plot shows the is the eQTL plot for one trait in the BXD liver proteome data. I briefly introduced that, and we plot the QTL plot from our model results compared to JAMA, and we may notice that they're actually quite close. And by comparing our fasting method, taking the null estimation of the heritability shortcut compared with JAMA, we notice that the null methods of our package gives lower loss scores. Actually, this is in terms of equivalent log base 10p compared to JAMA. But in our package, we do have efficient methods using similar shortcuts of the matrix modification that can estimate the h square independently for each marker, which we refer to as alternative here. And actually, this method gives us more closeness with the JAMA results. So systematically, we compare the runtimes and the accuracy, where the accuracy is in terms of the mean absolute value, absolute errors compared to JAMA results. And we show that our fastest method takes only about 3 seconds, 4 seconds for scanning over 32,000 of traits. And our most accurate results, which we refer as alternative grid, will give us the errors compared to JAMA within the 0.1%, and the runtimes is in like about 7 to 8 minutes, where JAMA, if we try to run JAMA on all of the traits, it will take a huge amount of time. So finally, to conclude my talk, our program, our software is fast for scanning over a large number of traits without sacrificing too much accuracy. And our integration in Julia makes it easier for the users to manipulate and use for analysis. And even if you don't, if you not ready to fully switch to Julia, Julia is easy to bind with other languages R and Python, and you may call our package in a active R or Python session. And we also support features of permutation testing, and and also like a Bayesian framework for estimating the heritability, including prior knowledge on the residual variances. So our limitations are that firstly, the matrix multiplication idea relies on testing of a single marker effect. And also we designed to carry out analysis for many traits, which can lead to insufficient sample sizes because it can be there can be difficulty to phenotype everyone for a large number of phenotypes. So that the insufficient sample size may lead to violation in the normal assumption. And our future steps is that our colleagues are working diligently to develop the front end of the package, and also we're working on the paper to be put on the link to be shared on the link if you would like to see more details. And finally, I want to thank our groups, the Center Research Group, Shanok, Gregory, and Harper. And I want to thank the G-Network groups for providing assistance to when we have data related issues. And I also thank Rob and Carl for providing advice regarding the project. And thank you all for listening. And I'm posting the QR code here. Hope it's large enough so you can scan from your phone. Then if you are willing, if you are interested in knowing more, and you can go onto the GitHub page, and if you have any issues, you can just contact me. Yeah.
Thank you.
Yeah. Thank you all.
We have time for one quick question.